Hello, welcome in video 29 in the lecture Advanced Mathematic Modeling. So we're discussing random walks, and in the last exercise I showed you an example of a biased random walk. So we throw a coin which has a bias. So with a certain probability we get +1 increment, with 1 minus q probability we get an increment -1. So this q gives us a bias. And then we've seen if we can calculate now the moments and the autocovariance function of this resulting of the increments and then of the resulting random walk. And when we have seen then, we get a walk where the average, the mean value increases with time, and we have some scatter. And when we have biased random walks, we have just to be careful that we not just calculate the second moment, because then if we just calculate the second moment, due to this bias, the mean square displacement, so the expectation of the second moment starts to increase diffusive, but later ballistically, because the mean linearly increases. But if we just instead use the variance instead of the mean, the second moment, then we just find the variance increases again as a square root of time, so it's a diffusive behavior. So when we have a biased random walk, we have to be careful that we always subtract the mean from the random walk. Okay, so but this was still a very trivial example because we had no correlations in the system, no memory. And now I want to introduce a random walk where we start to have a memory. So I will introduce a walk which is very similar to this, but has a slight twist which includes a memory. But before I do this, I just want to show you a weird example, a crazy example of a biased random walk. I just came across this, and it's so cool. I want to introduce it to you here, and probably I will make an exercise out of this. So what's the idea? So we make a random walk, so it's a kind of trading thing. So like you start with a capital, that's the money you have. Maybe you start with 1,000 euro, and now we make a bet. So we throw a coin, and then with 50% chance we have 50% increase in the capital, in your money. So x goes to 1.5x, so we would then get 1,500 euro. And again, with 50% probability, we have a 40% reduction in the capital. This means your capital goes to 0.6 times your capital. Now, so if you do this and you calculate now what's the main gain, so like here you would, in one step of this process, here you would, in this case you would have 1,500 euro, here you would have 600 euro left, so on average you will win. So this means on average we have a gain in the capital. Now the question is, would you repeat this process? So would you play this process against me or against the bank. So you make a lot of repetitions of this process. You always throw a coin, and either you gain 50% or you lose 40% of your capital. So that's a random. Then of course this is a random walk. And this walk is not biased here, because obviously this is not symmetric. But this random walk is different from the walks we had before, because the increments, so the step above or to the top or to the down, the steps, the width of the steps depends on the state x here. So in all the things that we did before, the increments did never depend on the value of the random walk. So it's a bit slightly different, but still it's a random walk. And then you can now make a. So the question is, would you do it against me? So you see, in every step of the walk, you have a gain in the expected money. Yeah, I mean, somehow this is one of these crazy examples where the intuition of most humans doesn't follow the way here. It just goes wrong. So let's see. I mean, like, do again one step, right? One step of the process. And so what's happening? So you have a capital X, and so with 0.5% we gain 50%. So then we have 1.5 times X, and with 50% we have 0.6x. So this is 1.05x. So means in every step we have a 5% gain on average. So if we have this random walk, and we have here the time, the number of iterations of the walk. We start with our 1,000 euro. And this means, on average, the expected value of the walk is increasing in time. And now you should do the simulations, and what you will see when you do simulations of the walk, you see as your money is going down. So your money actually is going to zero. So that was maybe you can never get negative, but if you simulate the random walk, your money is always going to zero after a long time. So how possibly can it be that we have a random walk where the expected value of x is increasing with time? So this is is just increasing, but actually, I mean, it's not even straight line. Like we have in every step we have this advantage, so it's actually increasing exponentially. So actually it's even increasing exponentially, but every realization goes down to zero. And so we will do this in the exercise, but I mean, if you see something like this and you have a real spirit of a scientist in you, you will stop everything else until you have figured out what's going on. The simplest thing is like maybe start doing simulations, make 4 lines of MATLAB code, calculate these trajectories, and convince yourself that the trajectories really go down to 0. And but the expectation you can calculate, and you can make many realization of the process and see what does the expected value in your realizations is doing, and how does it compare to the calculated value of this, and then what's going on in these examples, question mark. And I don't want to explain you more, because I think that's something you maybe better try to find out on yourself. Okay, so this was supposed to be just a very short remark. Now I see it's already 10 minutes. So with what I plan to do, I think I will do on the next video. Well, yes, thank you. For the moment, thank you.